node analysis, reference node shifting method. Yes or no? Okay. And I told you already that reference node shifting method will be very much advantageous in most of the cases. Especially when you have ideal voltage sources without any series resistors. Without any series resistors, you can do the problems easily with less number of equations with the help of reference node shifting method. Okay. And now we are very much comfortable in finding the minimum number of equations required to analyze the given network. Yes, there was a question asked in GATE, okay, that a network was given and what are the minimum number of equations required to analyze the given network. That was a question actually. So you must be in a position to identify the first instance, first glance itself, when network is given, you must be in a position to identify that. Okay, so yesterday I have taken two examples. Okay, so now let us see the third example here. Some examples, let us say. Okay. Now let us identify the number of equations required to analyze this network. Okay. See, this is some 10 volts, let us say, and this is 5 volts. And let's find the minimum number of equations required to analyze this particular network. Okay. So let's see now. Whenever a network is given, okay, whenever a network is given, first your focus must be on whether the network is having any current sources. If you have current sources, there is a possibility that you get minimum number of equations using mesh analysis. There is a possibility. I am not saying that you always get it. There is a possibility. There are no current sources. The mesh analysis is not the best method for this, because definitely 1, 2, 3 mesh analysis will give you how many equations here? 3. That's it. Now when it comes to node analysis, immediately your focus must be on whether network is having any ideal voltage sources without any series resistors. This is an ideal voltage source, doesn't have a series resistor. This is an ideal voltage source, doesn't have a series resistor. Okay. Therefore, this is an advantage. Now you can apply, reference node shifting method by properly choosing the reference node position. If you see, for example, take this one as a reference node, then what will happen here? This voltage will become what? 5 volt. And this will become what? V1. This will become what? V2. How many nodes are there? Total 4 nodes. Out of which, if this is selected as 0, this is going to be 5 volts. Yes or no? 4 nodes, 4 minus 1, 3 equations. Let us not come to such kind of conclusions. Because this network consists of what? 2 ideal voltage sources without any series resistors. Now, look at this V1, V2. These two are the principal nodes between which an ideal voltage source is connected. Okay? Without any series resistor, it leads to the formation of supernode. Yes or no? Okay? Now, how many equations you require? 2 equations you require with this particular reference node. Now, for example, you take this node as a reference node, for example. Then what will happen here? This is going to be what? Minus 10. Yes or no? Plus side you are taking 0, then it is going to be minus 10. Then now this will become what? V1. This will become what? V2. Again it is forming a supernode. Look at this, all of you. Again it is forming a supernode. Okay. So even though you shift the reference node, okay, using reference node shifting method, even though you shift the reference node position, still you are getting supernode case. You understand, all of you? Okay. What does it mean? Sometimes you cannot escape from supernode analysis. You understand, all of you? Sometimes you cannot escape from the supernode analysis. So therefore you must be careful here. Anyway, we are not escaping from the supernode. Why should we shift the reference node unnecessarily from here to here? Okay, we can directly take it. So what are the minimum number of equations required? Okay, in this particular problem using node analysis will give you 2 equations. How many number of nodes are there? 1, 2, 3, 4. How many equations are required? Not 4 minus 1, because ideal voltage sources without resistors are there. Therefore, that condition fails, n number of nodes, n minus 1 equations, and finally you got with the proper selection of reference node 2 equations. Understand? Okay. Now let us look at another example. Ten volts, 20 volts, 30 volts, 5 amperes, some resistor values are there. Now look at this, how many equations are required using mesh and node. So what are the minimum number of equations required here? 2. And by which method you are achieving that? Using node analysis in this context. You understand? Okay. Now in this case, 1, 2, 3, 3 minus 1, mesh analysis will give you 3 minus 1, 2 equations. Now node analysis, let us see now. And then we'll confirm which method is the best method. Whichever is giving less number of equations, that is going to be best method. Now, there are ideal voltage sources without any series resistor. Almost all, I think all these three sources are not having any series resistor. Yes or no? Now suppose if you select this particular node as reference node, what is this voltage? 30 volts. What is this voltage? Minus 10 volts. What is this voltage? Okay, 20 volts. Yes or no? Okay. That means there are 4 nodes, 1, 2, 3, 4. Don't come to a conclusion 4 minus 1, 3 equations. Okay. Before that you check whether there are any ideal voltage sources without series resistors. Yes, there are. Now if you take this, I know this voltage, this voltage, this voltage. I think I don't need to solve this network. Okay. Using any equation, I don't need any equation. So 0. Number of equations required to analyze this particular network is what? 0. You understand all of you? Okay. So this is how you need to analyze. When a network is given, on this spot, you must be in a position to identify the minimum number of equations using mesh, using node, and finally, what is the minimum of these two? That is going to be your answer. Okay. So please note down these 2 examples here. Quickly note down this. Put down this, right? Note down that. And meanwhile, I just give you the problems now. Now we have some problems, around 20 problems only on node mesh analysis. Let us try to solve them. Okay. Classroom workbook. Question number 1. The topic is what? Methods of analysis, node and mesh analysis. In that classroom workbook, question number 1. Please open that. In the topic, question number 1. Find VAB. What we do is, for first 2 problems, okay, we solve using both mesh analysis as well as node analysis. Understand? We solve using both mesh analysis as well as node analysis. Just to get the complete idea on how we are applying and comparison also. You come to know how we are able to solve a single problem using both the methods. Okay. First, let me take a simple problem. Okay. So I'm taking all the simple problems, keeping in mind all varieties of students, all categories of students. Okay. There are certain students are having still doubts in solving the networks. So please observe carefully. Okay. Now this problem, we will see this problem here. First mesh analysis. First mesh analysis. For mesh analysis, first you have to define what is the loop current. Yes or no? Now look at this. When you take minus 3i plus 10 minus 5i minus 8 plus 30 is equal to 0. Okay. You can also write when there is a single loop, total current is equal to total voltage by total resistance. That also, okay, that will also work out here. There is no need to write the equation directly. You can see the total current is nothing but total voltage by total resistance. But total voltage means you need to pick up all the voltages and take the algebraic sum of the voltages. Because the direction of the current is chosen like this, let us assume the 30 volts is higher. Now, similar to the same polarities, similar to the polarities here of 30 volts, whatever the polarities you have similar to this, you can add those two voltages. See, minus to plus, but plus to minus. That means 30 plus 10, but minus 8 I'm taking, divided by total path resistance, how much here? 8. So 40 minus 8, 32, 32 by 8, okay, 4 ampere. You understand? 4 ampere. So once you know the 4 ampere, what is the question actually here is asking? What is VAB? Yes or no? Okay. What is VAB? Now, let us find potential difference between 2 points. Once you know the loop current, you can find anything that you want. You can find powers, you can find voltages, you can find currents anywhere in the network. Potential difference between AB, start at A and reach B, use the touching concept, nothing but KVL, we have already discussed. A to B, you can proceed like this, or else you can proceed like this. If I proceed like this, let us say, what is the current flowing here? It is 4 ampere, okay? It is 4 ampere. What is the voltage here? 20 volts. 4 into 5, 20 volts. Use the touching concept, okay? What do you get here? VAB. VAB will be, okay? VAB will be plus 20 and plus 8. 28 volts. That's it. Okay? The same network we will take and apply node analysis here. Okay? So node analysis when we apply, look at this, minus plus. Ten volts, 8 volts. Okay? Let's see now. You want potential difference between 2 points here, VAB. Suppose if you take this one 0, can't you take this one as VAB directly? Yes or no? Okay, you can take, right? Then what do you get here? VAB, this is node analysis, okay? VAB minus 8 by, normal equation I'm writing. Later I will write inspection also, okay? By 5 plus VAB minus 10 minus 30 by 3 is equal to 0. You can write inspection all the time you try to practice the inspection, okay? So VAB of 1 by 5 plus 1 by 3 is equal to touching positive first plus 8 by 5. Touching positive and touching positive. There are two sources. You must take both of them, okay? So 10 plus 30 by 3. That's it. So just solve it. You will definitely get 28 volts. Understand all of you, okay? Please take down. Please take down. Take down that. Please take down that. Meanwhile, I will note down another problem. Classroom workbook. Question number 2. Question number 2. Let us see how many varieties of methods that we can apply. What are the various ways to solve the network? Let us investigate. Okay, initially we investigate all the methods to get the flexibility in solving the problem. Okay, you get different ideas once you come across a new problem. You will automatically get instant ideas if you investigate initial stage various methods to solve the problem. Okay. So I think you finished this part. Okay. Okay. So please note down the second question as well. The question is here, read the question, determine V1 and V2 values, right? What is the second question? Determine V1 and V2 values. So let us apply both mesh analysis as well as node analysis. Let us see how many ways are there to solve this network. It's a very important case, important problem to understand, okay? Various methods. Now let us see first mesh analysis. Okay, mesh analysis. How many equations you require to solve this network using mesh analysis? 1, 2, 3. 3 minus 2. Only one equation is enough. How many equations you require using node analysis? 1, 2, 3 and 3 minus 1, 2 equations enough. Yes or no? So mesh analysis will give you one equation. Node analysis will give you 2 equations. Minimum number of equations required is what? 1, and that you can achieve through mesh analysis. Therefore, which is the best method for this particular problem? If I ask you the question, what is your answer? Mesh analysis is the best method. Yes or no? Obviously. But let us solve this problem using both the methods and we'll see. Okay, some important observations we'll see. Now, I told you to get that minimum number of equations in case of mesh analysis, I told one instruction. What is that? I gave one instruction. What is that? That each current source must experience one and only one loop current. There is no other loop current passing through it. Okay. Now, here also 4 amperes. It is 4 amperes if no other loop current is passing. It is 1 ampere if no other loop current is passing through the current source. Then the remaining loop I can select directly here I. Yes or no? Okay. Therefore, now you see here. Now let us apply KVL in this loop. This already we know. This already we know. Let us apply KVL in this loop. Tell me, minus 6i. Minus 7 of what? I greater, let us assume, I minus 4. Minus 2 of I minus 1, yes or no, is equal to 0. So if you just solve it, now what do you get here? Minus 6i, minus 7i, minus 2i. Minus 7 minus 6 is nothing but minus 13. Minus 13 and minus 2, minus 15. minus 15i. Yes or no? Okay. Now minus of minus plus, that is 28, and minus of minus plus, that is 2. Okay. So plus 28 and plus 2 is equal to 0. So I will become, okay, minus 30 by minus 15, right? 2 amperes. You understand, all of you? Okay. Now let us find the V1, V2 using this current. What is actually V1? V1, is it not voltage across 2 ohm? See, node voltage will become a branch voltage somewhere. Where is that going to be? Tell me. Node voltage will become branch voltage across an element, okay, across an element which is connected between the principal node and the reference node. This is an element which is connected between principal node and reference node. Its branch voltage will be same as the node voltage. This is an element which is connected between second node and reference node. Its branch voltage will become, okay, same as the node voltage. Understand? That means I can say the voltage across 2 ohm is V1. I can say the voltage across 7 ohm is V2. Clear? Now, let us find that V1 value something like this. This is 2 ohm. So what is the current flowing here? I can say downward direction if I want 1 minus I, upward direction if I want I minus 1, anything is okay. But place the polarities according to the direction chosen. Now I am choosing the downward. Let me say it is 1 minus I. What is this 1 minus I? I is 2 minus 1 ampere. Okay. Now what is the voltage across it? Okay. What is the voltage across it? Now V1 will be minus 1 into 2, okay, minus 2 volts. Yes or no? Okay. V1 will be minus 1 into 2, okay, yes or no, all of you. Now with this current, otherwise you can analyze like this. Suppose for example, all of you look at this once, okay. Because of this current, what is the voltage across this? Minus 1 into 2, that is minus 2 volts. But how you want the voltage with this plus minus, right? V1. You want desired polarities plus minus, actual polarities plus minus. There is no mismatch. Therefore, I can take the value as it is. Okay. Next, V2. What is the current flowing in the downward? I minus 4. I minus 4 is nothing but what? 2 minus 4, nothing but minus 2 ampere. Because of this, what is the voltage across this particular element? Minus 2 into 7, minus 2 into 7, minus 14 volts. Okay. But how you want the voltage to be measured with the polarities plus minus V2? Actual polarities, desired polarities, no mismatch. Therefore, take as it is minus 14 volts. You understand, all of you? Okay. This is how you can find using mesh analysis. So first you please note down this, then I'll go for, okay, node analysis. First you note down this quickly. So meanwhile, I just note down the problem once again for node analysis. This is method 1. Method 2. Method 2. Node analysis. Node analysis. For this problem, look at this all of you. For this problem, okay, there are two variables, right? Now, can I apply node analysis here? What do you get? V1 by 2, V1 minus V2 by 6 minus 1 ampere. Yes or no? Second equation, please. V2 by 7, V2 minus V1 by 6 plus 4 ampere. Clear? I can apply directly the inspection. Inspection 2 by 2 matrix. Yes or no? So 1 by 2 plus 1 by 6. Here 1 by 7 plus 1 by 6. Who is the common element here? 1 by 6. Therefore minus. Okay, all off diagonal elements will be having negative, diagonal elements positive in case of node analysis. Into V1, V2 is equal to, now this is an entering current, plus 1. That is a leaving current. Outside always negative, right? So that's it. V1 is equal to delta 1 by delta, which you get minus 2 volts obviously. You can please check at your leisure time. You get the same answer because you're already having the answer. That's why I'm noting down. Delta 2 by delta minus 40 volts. Understand all of you? Okay. This is how you apply. Okay. Using Cramer's rule, you can find the determinants and then find V1, V2 values. This is using node analysis. Okay. So please note down that step. Okay. We will see another method also. Method 3. These are all important investigations. Okay, to see how many ways are there to analyze a given network. This experience will surely help you a lot in solving so many problems, and in GATE little bigger size problems are being asked, particularly in recent years. Okay, the size of the network is taken always in a big size, so one must be really good at analyzing the network in less amount of time. That is why I'm trying to tell you all the methods here. I think you have written this part. Okay. Now, all of you look at this. Don't write anything. I think you have written this part, right? Okay. Please look at this. I'm going to give you some valuable inputs here. Okay. Look at this. Suppose, you see here, suppose if you transform this particular part, the current source with a parallel resistor can be transformed into what? A voltage source with a series resistor. Now, once the transformation is done, the resulting network, how it looks like? The 6 ohm, 7 ohm, and the voltage source. What is the value of the voltage source? 7 into 4, 28 volts. Polarities, please, minus plus, because downward direction current. So, this 6 ohm, 7 ohm, and 28 volts, how they look like? They are all in series. Yes or no, all of you? Okay. When all elements are in series, do you need to take this V2 variable? Not required. So you can solve V1, and once you get this V1, you can jump from this point to this point using jumping technique. You understand, all of you? Okay. That means the same problem can be solved by using a single equation with the help of node analysis, exploiting or utilizing this opportunity, source transformation. Understand, all of you? Okay. But if somebody is asking what are the minimum number of equations required using node analysis, what is your answer? 2 only. Okay, that answer must be given without any reduction, without any transformation. As it is, the network must be taken and tell what are the minimum number of equations required to analyze. Definitely 2. But if given an opportunity to solve this network, use the same node analysis and utilize this transformation and solve with only one equation. Understand, all of you? So minimum number of equations required using mesh analysis, 1. Minimum number of equations using node analysis, 2. Then if somebody is asking solve using node analysis, then you can utilize that opportunity of transformation and solve it by only one equation. So I'll do that using source transformation using source transformation, the network looks like this. Okay, so since it is first time I'm drawing everything in detail, but next time onwards on the network directly you are supposed to attack. So this is minus, this is plus. What is this? 28 volts. Okay, 7 4 ja, 7 into 4, right? What is this? 7 ohm. This is 6 ohm. And what about this? This is 2 ohm, right? Okay, this is 1 ampere. Now I solve this. Here V1. Now V1 off. Let me use again inspection. Transformation, inspection. If you are able to apply both at a time, I am sure that you can save a lot of time. 1 by 13. Hope you understand why I am taking 1 by 13. 1 by 2 is equal to, touching negative first, minus 28 by 13. And this is entering current, plus 1. Yes or no? Inspection, it is plus 1 entering current. Therefore, if you solve this, you get V1 is equal to minus 2 volts. Understand all of you? Okay. Now, I would like to find V2 also here. Okay, V2 I would like to find. To find V2, I jump from this point to this point. I told you already, if you are good at jumping technique, you can solve a problem. 2 equation problem can be converted into 1 equation problem. Exactly the same thing I'm doing here. To find this variable, I'm using jumping technique. Okay, to jump from this point to this point, I must know the voltage. Yes or no? To know the voltage, I must know the current. What is the current? V1 plus 28 by 13. Yes or no? Look at this current. This current is V1 plus 28 by 13. But what is V1 actually here? Minus 2 plus 28, 26 by 13. That means 2 amperes. Now 2 amperes. Okay, let me take this as a source transformation here. 2 amperes. Therefore, this will become what? 6 into 2, that is 12 volts. Now jump from this point to this point. You are jumping from higher potential to lower potential. Therefore, drop the voltage or take the voltage. Drop the voltage. Now minus 2, minus 12, you are getting minus 14 volts. You understand all of you? Okay. See, a 2 equation problem has been converted to what? A single equation. Okay, the node analysis, utilizing the source transformation and also utilizing what actually here the jumping technique. If you know one node voltage, you can easily find the other node voltage jumping from the node where the voltage is known to the node where the voltage is to be determined. Okay, you understand all of you? Please do that. All these experiences will apply in upcoming problems. Okay, because it is we are in the beginning. Please make it fast. Just an extension. Method 4. The same source transformation I'm applying on both sides. Okay, the same source transformation I'm applying on both sides. Just now we applied only one side. See, you can apply either this side or this side. Apply this side, find V1 and jump from this point to this point. Or else, apply this side, find V2, then jump from this point to this point. You get the same answer. Or else, apply both sides. Okay, apply both sides. What do you get here? If you apply both sides, you get plus minus. This is 2 into 1, right? 2 volts. What is this? Minus plus, right? 28 volts, 7 ohm, 6 ohm, and 2 ohm. If this is 0, and this is actually V1, right? This is V2 given. Look at this. This is V1, this is V2, right? The same V1, V2. Now, since it is 0, you already know the voltage here how much? 2 volts. Now you can jump from this point to this point. To jump from this point to this point, you must know the voltage here. To know the voltage, you must know the current here. For that, let me find the current I. So what is I? I is equal to 2 minus of minus plus. right? Yes or no? Because this is 2, 2, and if this is 0, this is minus 28. Or else you can take directly single loop, right? Minus plus, both are having the same polarities, right? 30 plus 2 plus 6 plus 7, how much it is? 2 ampere. Okay. Now if 2 amperes is flowing here, what is the voltage? 2 into 2, 4 volts. Yes or no? Jump from this point to this point. Now 2 minus, because drop the voltage higher to lower, therefore minus 2 volts. Now if this is 0, this is what actually minus 28 volt. Jump from this point to this point, and you already know the voltage here. How much same 2 ampere current is flowing? Yes or no? Same 2 ampere current is flowing, 2 into 7, 14 volts. And now you are jumping from this point to this point, lower to higher, take the voltage. So minus 28 plus 14, nothing but minus 14 volts. Okay, so there are different varieties of ways to solve the network. Okay, because we are in the beginning, I'm trying to explain all different possible ways to analyze the network. But the next problems, I'm not going to do that. Whichever is the best way, we will just smash with that method. Okay, come on, please note down that. Note down. Classroom workbook, question number 3. Find V naught, I naught, and also power of 50. Okay. Find V naught and I naught. Okay, I think those two are enough. Okay, in this question only those two are asked. Okay, find V naught and I naught. Find V naught and I naught. Okay, so please go to the question number 3, classroom workbook. So I think you finished this part. Okay. Now let's try to analyze the networks. Single source network, probably you can solve it using simple current division, voltage division. There is absolutely no doubt. Okay, that you try on your own. But now my intention is how to apply using node analysis and mesh analysis here. Okay, single source usually can be solved. Okay, but look at this. Now, how many equations you get using mesh analysis? 3. Yes or no? How many equations you get using node analysis? 1. These two are same, right? 2, and this is 3. Yes or no? Okay. There are 3 nodes, but 3 nodes, 2 equations before you conclude that, okay, 3 nodes, 2 equations. Before you conclude that, better you check whether there are any ideal voltage sources without any series resistor. Yes, there is a voltage source without any series resistor. Then n number of nodes, n minus 1 equations, n minus 1 equations, that condition violates, that condition fails. Now it all depends on how you select the reference node. If you select this one as a reference node, you obviously know the voltage here, what, 50, okay, 50 volts. And out of these 3 nodes, you do not know only one node voltage, that is what here. What is that? Say this is V0, because already V0 is given, that's why I am taking V0 directly here. Okay. Now let us apply node analysis here. Tell me, V0 minus 50 by 30, V0 minus 50 by 70, V0 by 5, V0 by 20. That's it. So V0 minus 50 by 30 plus V0 minus 50 by 70 plus V0 by 5 plus V0 by 20 is equal to 0. Let us apply inspection. Here is one interesting point to be observed in the inspection. Look at this. V0 of 1 by 30, 1 by 70, 1 by 5, 1 by 20. Yes or no? Is equal to. You must observe one important point in the inspection. This is a special case. What is that special case? The special case is this particular node voltage is a constant value. It is not a variable. If it is a constant value, you must take this constant value divided by whatever the resistor is connected to this particular node. You are supposed to take plus 50 by 70 plus 50 by 30. Directly you take the value. It is plus 50, right? Plus 50 by 70 plus 50 by 30. How many elements are connected here? Only 2 elements. That's it. 50 by 70, 50 by 30. You can also even generalize like this. This is 0, 0 by 20, 0 by 5. That's why we don't write it, because you are getting 0. I hope you understand the point. Now, from this, you can get what is the value of V0. Please calculate that quickly. Okay. V0 value. You can calculate that. Okay. I think all of you understand this, how I am taking 50 by 70, 50 by 30. Why I am taking 50 by 70, 50 by 30? Because this is a constant. This is not a variable. You can also investigate here, minus 50 by 30. If you send it outside, 50 by 30. Minus 50 by 70 plus 50 by 70. See, I am applying inspection based on my past experience, based on my observations in the past, by solving several number of problems. Now I conclude that when you have a constant, you are supposed to take this. This is a very important case. Most of the times when you apply inspection, you may forget this. Okay. So this is very important here. Now V0 value, if you find, you get definitely 8 volts. So once you get 8 volts, okay, V0 is already coming here. And what is I0? What is I0 actually in this path? This is the zero resistance path, right? Okay. See, this is the zero resistance path. There is no potential difference, but there might be current in the path. Okay. Voltage 0 does not mean that current 0. Particularly in short circuit, you cannot apply Ohm's law to that. Okay. You cannot apply Ohm's law to the short circuit, I'm telling you. In the short circuit, voltage might be 0, but current may exist. In the open circuit, okay, current may be 0, but voltage may exist. Understand all of you? Okay. So what is that current? How do you find? In whichever the path you want to find the current, I told you, first you identify whether that path is consisting of a resistor or not. If that path is having a resistor, apply Ohm's law. Otherwise, you go for KCL. Okay. So, is it having any resistor? No. Therefore, you apply KCL. Let me take node A. KCL at node A. KCL at node A. Understand all of you? Okay. So, tell me, I0 is entering. V0 by 5 is leaving. V0 minus 50 by 30 is leaving. Substitute here 8 by 5 plus 8 minus 50 by 30. You can simplify it. Okay, I give you that answer directly here. That must be 0.2 ampere. That's it. Okay. Please note down. This is how you can solve using node analysis. It's very important.